Why are there not more people talking about the invisible foundations of matter? This is gonna blow your mind. Welcome to Intersidera Versor. Everything around us is made up of tiny particles. These particles are so small that we cannot see them with our eyes. They make up all the matter in the universe, from the air we breathe to the stars in the sky. These particles are called atoms. Atoms are the building blocks of everything we see. If you took a single atom and placed it next to a grain of sand, it would be like comparing a grain of sand to the entire Earth. Despite their small size, atoms are incredibly important. They define the properties of everything around us. Without atoms, nothing would exist. Atoms are made up of even smaller particles. These smaller particles are called subatomic particles. The main subatomic particles are protons, neutrons, and electrons. Protons and neutrons are found in the center of the atom, while electrons orbit around the center. Atoms are not just tiny particles floating around. They have a complex structure. This structure determines how atoms interact with each other. Understanding atoms and particles helps us understand the world at a fundamental level. An atom is like a miniature solar system. At the center of the atom is the nucleus. The nucleus is made up of protons and neutrons. Protons have a positive charge, while neutrons have no charge. Together, they give the nucleus a positive charge. Electrons orbit around the nucleus. They have a negative charge. Electrons are much smaller than protons and neutrons. They move very fast, creating a sort of cloud around the nucleus. This electron cloud gives the atom its size and shape. The number of protons in the nucleus determines what element the atom is. For example, an atom with 1 proton is hydrogen. An atom with 6 protons is carbon. The number of protons is also called the atomic number. This atomic number is unique to each element. Neutrons add mass to the atom but do not change its chemical properties. Atoms with the same number of protons but different numbers of neutrons are called isotopes. Isotopes can have different physical properties like stability and radioactivity. The periodic table is a chart that organizes all known elements. It arranges them by their atomic number, which is the number of protons in the nucleus. The periodic table helps scientists understand the relationships between different elements. Elements in the same column, also called a group, have similar properties. For example, the elements in the first column are all metals that react with water. Knowing the properties of one element helps predict the properties of others in the same group. The periodic table also shows trends in properties as you move across a row or down a column. For instance, elements become more metallic as you move from right to left. They become more reactive as you move from top to bottom. These trends help scientists understand how elements behave. Each element on the periodic table has a unique symbol, usually 1 or 2 letters. For example, H stands for hydrogen and O stands for oxygen. This shorthand makes it easier for scientists to write chemical equations and communicate about different elements. Atoms bond together to form molecules. There are 2 main types of chemical bonds, covalent bonds and ionic bonds. Covalent bonds form when atoms share electrons. Ionic bonds form when one atom gives up an electron to another atom. The positive and negative charges attract each other, forming a bond. For example, sodium and chlorine form sodium chloride, NaCl, or table salt. Different types of bonds give molecules different properties. Section 5. The evolution of atomic theory. The concept of the atom has a long history. The idea dates back to ancient Greece. The philosopher Democritus first suggested that everything is made up of tiny, indivisible particles called atoms. However, this idea was not widely accepted until much later. In the early 20th century, scientists began to uncover the true nature of atoms. J.J. Thomson discovered the electron in 1897. His experiments showed that atoms are not indivisible, but contain smaller particles. This was the first step in understanding atomic structure. Ernest Rutherford made another breakthrough in 1911. He conducted experiments that showed the atom has a small, dense nucleus. His work revealed that the nucleus contains protons and neutrons surrounded by a cloud of electrons. This model of the atom is still accepted today. Niels Bohr further refined the model in 1913. He proposed that electrons orbit the nucleus in specific energy levels. This model helped explain the behavior of atoms in chemical reactions. Together, these scientists laid the foundation for modern atomic theory. Section 6. Quantum Mechanics, the New Frontier. Quantum mechanics is the study of particles at the smallest scales. It has revolutionized our understanding of atoms. In classical physics, particles follow predictable paths. But in quantum mechanics, particles behave in strange and unpredictable ways. One key concept in quantum mechanics is the probabilistic nature of particles. Instead of having a definite position and speed, particles exist in a range of probabilities. For example, an electron does not orbit the nucleus like a planet orbits the sun. Instead, it exists in a cloud of probabilities called an orbital. Another important idea is wave-particle duality. Particles like electrons can behave both as particles and as waves. This dual nature was demonstrated in experiments like the double-slit experiment. Quantum mechanics also introduces the concept of quantized energy levels. Electrons can only exist at specific energy levels, not in between. This explains many chemical properties and reactions. Quantum mechanics has many practical applications. It is the basis for technologies like lasers, transistors, and MRI machines. Understanding quantum mechanics helps scientists develop new technologies and solve complex problems. Section 7. The world of quarks and the Standard Model. Atoms are made of protons, neutrons, and electrons, but these particles are not the smallest units of matter. Protons and neutrons are made of even smaller particles called quarks. Quarks come in different types or flavors, such as up, down, charm, and strange. The Standard Model of particle physics describes how these particles interact. It includes quarks, electrons, and other particles like neutrinos and bosons. The Standard Model explains 3 of the 4 fundamental forces of nature: electromagnetic, weak, and strong forces. It does not include gravity. The discovery of the Higgs boson in 2012 confirmed a key part of the Standard Model. The Higgs boson gives other particles their mass. This discovery was made at the Large Hadron Collider, a powerful particle accelerator in Switzerland. Despite its success, the Standard Model is not complete. It does not explain dark matter, dark energy, or gravity. Scientists are still searching for a deeper understanding of the universe. The study of quarks and the Standard Model is an ongoing and exciting field of research. Section 8. The mysteries of dark matter and dark energy. Dark matter and dark energy are 2 of the biggest mysteries in science. They make up most of the universe, but we cannot see or touch them. They do not emit light or energy, making them invisible to our instruments. Dark matter's presence is inferred from its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Dark energy makes up about 68% of the universe. It is causing the universe to expand at an accelerating rate. The study of dark matter and dark energy is crucial for understanding the universe. Section 9. Practical applications of particle research. Understanding particles and atoms has many practical applications. One of the most important is nuclear energy. Nuclear reactors use the energy released by splitting atoms to generate electricity. This process is called nuclear fission. It provides a large amount of energy with relatively low emissions. Another application is in medicine. Particle research has led to the development of new diagnostic and treatment techniques. For example, PET scans use positrons to create detailed images of the body. Radiation therapy uses high-energy particles to target and kill cancer cells. Particle research is also important in materials science. Understanding atomic interactions helps scientists create new materials with specific properties. For example, semiconductors are made from materials with controlled electrical properties. These materials are essential for modern electronics. These practical applications show the importance of particle research. They improve our quality of life and drive technological innovation. Continued research in this field will lead to new discoveries and applications. Section 10. The future of atomic exploration. The study of atoms and particles is far from over. Ongoing research is pushing the boundaries of our understanding. Scientists are working on new theories to explain dark matter, dark energy, and gravity. These efforts could lead to a unified theory of physics. New technologies are also being developed. Powerful particle accelerators like the Large Hadron Collider allow scientists to study particles at higher energies. These experiments could reveal new particles and forces. Advances in quantum computing are another exciting area. Quantum computers use the principles of quantum mechanics to perform calculations much faster than classical computers. The future of atomic exploration holds great promise. It will help us solve fundamental questions about the universe. It will also lead to new technologies that improve our lives. The study of atoms and particles is a fascinating and important field of science.